So this is lecture 2 in U22158. Excuse me. We're going to expand on the chemistry and introduce some other topics and concepts as we go along. So we've laid the foundation in lecture 1, and we're going to look at some more examples and expand the arena of pharmaceutical product formulation stability. We haven't discussed this previously, dimerization and polymerization of actives and pharmaceutical excipients, for instance. A definition of dimerization or polymerization. Dimerization would be two molecules interacting and binding covalently to each other. Polymerization would mean multiple molecules reacting with each other and covalently binding. We met amoxicillin previously, we met penicillins previously undergoing hydrolysis of the beta-lactam ring. However, there's further reaction that can occur with the beta-lactam once it's hydrolyzed. And this tends to happen in concentrated solutions that are decomposing, and the decomposition can continue to form oligomers, oligo instead of poly, trimers, tetramers. So you would go dimer, trimer, tetramer, and so on. Okay, so what we're going to look at now is amoxicillin degradation. We have an amide bond, as we've met previously in the penicillins, that can undergo hydrolysis, and when the molecule undergoes hydrolysis, it releases a carboxylic acid, the orange oval, and the presence of the amino group, which is in the light blue here, and the fact that if we take the fact that two molecules have decomposed, those two molecules can now react with one another to form a new amide bond, hence multimerization. Now you can see that process can continue because we still have a beta-lactam ring in the dimer. Glutaraldehyde. Glutaraldehyde can be present in formulations, I believe as a stabilizing agent and an antimicrobial. And glutaraldehyde can undergo degradation by polymerization, and there is a pH dependency of this polymerization. If I go to the chemistry slide, it's probably easier than talk through the text. You can always go back to the text. So glutaraldehyde has a keto and an enol form, and these are in equilibrium, and the keto and enol form are reactive towards one another, and you can see that glutaraldehyde can dimerize to a product. This can carry on again because we can have keto and enol tautomerism forms, and you get polymerization, and the reaction carries on. And this would take glutaraldehyde out of a formulation, and as the polymer carried on being formed, you would see a degradation of a formulation. So we've talked about polymerization and oligomerization. Isomeric changes occur within chemical structures as well, and we haven't dwelt on this yet. So different isomers of a drug often have different pharmacological activity and toxicity. So we have to be mindful of the fact that whenever we have an isomeric center in a molecule, that this can change during storage, during preparation of formulation and its lifetime. Conversion of optically active molecules with one chiral center into a mirror image is known as racemization, if that occurs. If there are more than one chiral center, you get diastereomers, and these can interchange as well, as long as the centers are prone to conversion. We've seen epinephrine before, and we obviously realise that epinephrine's got a bit of a problem as a drug, hasn't it? So what I'm going to do is go to the chemistry slide. You can always go back to the text and read through it at your own time. So here is epinephrine, and we already know that there's problems with epinephrine in terms of its oxidative stability, but it also undergoes an epimerization or a racemization. Here is our active, optically active center, and depending on the pH of the formulation, this center, being next to an aromatic ring, is very prone to SM1 type, E1 type elimination, and that's what's happening here. A molecule of water is leaving a cation that's benzylic, and that means that's fairly stable and quite easy to produce. And then this structure can be reattacked by water under the influence of acid to go back to go to this alcohol. Be mindful of the fact that that water can attack either side of that double bond when it goes back in, and can give this or this. Therefore, you would end up with a 50-50 mixture of epinephrine enantiomers. Epimerization can occur in other drugs as well, and we have this drug. Tetracycline has multiple chiral sites, but its epimerization occurs in this position to generate 4 epitetracycline, and again, the reason why this probably comes about is the proximity of this chiral center to this enolic delocalized chemistry around here, which makes that position prone to departure and recombination. A bit like that happened with epinephrine. And this epitetracycline is no longer active against microbes, and in fact is toxic. Other isomers can undergo conversion, and retinol, in this particular couple of slides we're going to use retinol as an example, and let's have a look at retinol. So all trans retinol, which is the pharmaceutically active component of some formulation, some drugs, can undergo isomerization into its various cis isomers. So what we're getting is a cis trans isomerization around a double bond. Now that can happen around the 13 position double bond or around the 9 position double bond by either light or heat, which suggests that this one is more facile than this one. If this one requires light, it's a higher energy process. If this one requires only heat, it's a fairly low energy thing for that conversion to occur. So we've had polymerization, we've had optical isomer conversion, epimerization, we've had geometrical isomerization, and now we're going to look at photodegradation. And we've seen the effect of light before. We've seen the effect of light before, and remember that photolysis tends to be linked or is often linked to oxidation, and that photodegradation can occur and needs to be prevented by colouring bottles, etc., excluding light. And we've seen examples of that before, remember. Protein conformation changes can occur. So if you have a protein containing formulation, proteins may change their 3D structure by denaturation, and this can happen if the compound's accidentally been frozen, for instance, which is what you would have thought is a protective thing, putting a protein solution in the freezer rather than putting it in a fridge, which is maybe indicated on its storage conditions. You can actually denature a protein by this method. So you have to be aware that that can occur. Okay, chemical incompatibilities within formulations is something that you should be aware of. And drug degradation can be due to the presence of another drug within a co-formulation, or the excipient and those drugs within that formulation. It depends how complex the formulation is. So here we have an example of paraben, which is a preservative, and paraben can interact with sorbitol to produce sorbitol hydroxybenzoate esters. So this can decrease preservation activity within a formulation. So you've probably met the paraben or benzoate esters before, hydroxybenzoate esters as preservatives, and sorbitol would be a non-sugar sweetener, and sorbitol is used for other reasons as well in formulations, and you can get reactions across those two, and we'll look at another example that explains that chemistry in a moment. Aminophylline, which is a complex between theophylline and ethylene diamine. Ethylene diamine is added to a formulation, and that increases the solubility of theophylline within suppository bases. The melting point of the base increases above physiological temperature, and that prevents release. Okay, so amide bonds form between ethylene diamine and carboxylic acid groups of fatty acids. We've actually seen that type of chemistry in the antibiotic dimerization. So this is not an unexpected process, an amine reacting with a free carboxylic acid. The reaction that I was discussing here, which is sorbitol reacting with paraben, is actually an example of a transacetylation as well. And transacetylation is when an acetyl group is transferred between one molecule and another. There is a tablet formulation of aspirin with phenylephrine, a hydrochloride, and the acetyl group gets transferred to phenylephrine from aspirin. That can also occur between aspirin and paracetamol. And aspirin can also react with polyethylene glycol bases, because polyethylene glycols are only polyalcohols after all, and PEGs can be used as a base for suppositories. The Maillard reaction is a reaction that actually you've all witnessed. When you cut an apple and an apple goes brown, this is known as a browning reaction, and in fact what's happening there is a Maillard reaction. This is free amines within a system and reducing sugars that can occur, and this is responsible for the browning of cooked foods and also the browning of apples. So an amine drug and lactose or other sugars can lead to yellowing of tablets, and we've mentioned that discoloration of formulations can be an issue in terms of compliance. People don't like off-coloured formulations. And the only way to get around that is to maybe replace with an alternative diluent other than that containing lactose. Dispersible tablets need sweeteners in often, and if an amine is present, then sucrose and glucose will undergo a Maillard reaction with these amines, whereas mannitol, for instance, will not undergo the reaction. So you have some options to get around that chemistry. Okay, with all these problems that we've met, the chemical instability. So we've set the scene in lecture 1. We've looked at the full range of chemical instabilities in drugs and excipients now. And we have mentioned about possible ways to combat these issues. Pharmaceuticals should be formulated and stored to minimize degradation. The factors that affect degradation are temperature, solvent that the formulation is in, acid and bases present within the system, the ionic strength of a system, particularly when it's in solution, obviously, the presence of light, and the presence of oxygen. So you should always remember that these are the key indicators that you're looking for to control. So we know that temperature accelerates degradation. So products that are unstable at room temperature, there's an option of storing them in a refrigerator between 2 and 8, and that has to be carefully controlled. It's no good putting a refrigerator into a hot room in a storage facility within a hospital. When that room gets incredibly hot, the refrigerator will not cope, and the temperature will drop. Will raise above 2 to 8 and affect stability. And that's been a practical issue that's come to the university as a problem. Sometimes products can be stored in a freezer, but we know that certain situations of freezing things can cause issues, for instance the proteins. But storing in a freezer is possible. Storage and distribution is inconvenient because you know what it's like when you get things out of a freezer. They're often coated with frozen water. Liquid products need to be thawed before administration, but risk of degradation if there's heat source used to thaw them. So pre-planning must be taken into account. There are exceptions to storing in freezers, and we've met that before. Amoxicillin is actually less stable when frozen than when refrigerated for a variety of reasons, and that has to be taken into account. And we can see that protein-based products and vaccines shouldn't be frozen wherever possible. So what this really means, what's the take-home message on this slide? Follow the storage instructions. Don't think that freezing something can be better than just putting it in a refrigerator, and also, of course, vice versa. We met that hydrolysis is the most common chemical degradation reaction if the pharmaceutical is dissolved in water. The aqueous solvent can be replaced with a non-aqueous solvent, and that has its own issues. The dielectric constant of the solvent will have to be taken into account. A higher value means it's more polar, and this dielectric constant and the nature of the solvent can influence the rate at which a charged species react, for instance. The effect of dielectric constant usually outweighed by compatibility with drug or toxicity of solvent. Tablets and capsules are more stable than liquid dosage forms. However, reactions can occur on the surface of the solid dosage form, as we've met before, and we know the nature of that water, that extra water. We've talked about it previously, and you can actually smell these. There are occasions where you can sense that something's not quite right, smelling acetic acid from a compound. And this is quite common in a chemical laboratory, by the way, when you get acetates or ethanoates. You know when they've gone off if you can smell acetic acid coming off them. Penicillins are unstable, and therefore they're formulated as freeze-dried powders to remove water and then reconstituted before injection. That's common. So reconstitution of a dried powder, freeze-dried powder, can be useful. And suspensions are more stable than solutions because the drug is protected in an insoluble particle. Acid and base catalysis of chemical processes. We've already met examples of where acid and bases can influence the degradation of compounds. And there has to be studies undertaken where functional groups are prone to, say, acidic or basic catalyzed degradation products, where pre-formulation would have to explore the degradation against pH. Here's some examples of pH profiles, and what you would do is you would plot the log of the first order reaction rate constant for a decomposition against pH, and this gives you a plot that gives you information about the decomposition, and you can see that there are slightly different forms. You can have very sharp responses to pH or very broad responses. So these are antibiotics here. And then aspirin, you can see, actually seems to have a bimodal response to pH, and that's because aspirin undergoes ionization on producing a product. And then other drugs will have their own unique pH profiles. The take home from this slide, be able to plot log 10, base of log 10 first order rate constants against pH, or at least have some commentary on the form of the curves. Other species beside hydrogen and hydroxyl ion can generate acid and base catalysis, so you have to be a bit careful. Buffer ions are a common cause, so careful selection of a buffer within a formulation is required, and you've met buffers elsewhere. Hydrolysis of an amide bond of chloramphenicol, for instance, is catalyzed by common buffers, including the presence of phosphate and its conjugate acids and bases, and acetate, which are the common buffers. Borate buffer does not cause catalysis, so is used in the eye drop formulation, and this is due to the position of the buffering species, but also the nature of the buffering species. Ionic strength. Changing the ionic strength by adding more electrolytes can have some influence on degradation reactions. It depends on often the polar nature of the drugs or the excipients, and adding more electrolytes can influence this rate. But often it's not so important to include in formulation studies, but it is something that you need to bear in mind. However, if you are looking at pre-formulation studies of a drug stability or a formulation stability, ionic strength of buffers should be kept the same throughout all replicates of any experiments that you undertake, because this can influence the reactions. Light, well, we've now mentioned this maybe 3 or 4 times, so I'm not going to dwell on that slide. Oxygen, we've actually mentioned that 3-4 times now. The presence of oxygen, obviously, we've said can be modulated by the presence of redox sensitive ions, and the use of chelating agents can control those processes. Physical instability, mostly due to this occurs when physical changes in the dosage form occurs. It can spoil the appearance of particular formulations, tablets, suppositories, and so on. It reduces the effectiveness if you actually get a physical instability within a formulation, and loss of drug due to absorption or evaporation from a system, and contamination of product due to extractives. And this table really encapsulates all these physical instabilities that can occur. So appraise yourself of the formulation type and the physical instability that may happen and affect on the actual dosage form. This is worth spending some time on. Absorption. Absorptions of molecules into plastic or rubber containers or closures that contain a formulation can occur, and this means that the drug or excipient can move onto a surface, and non-polar molecules are susceptible to absorption onto plastics and rubber. So if your drug or excipient is particularly apolar, it will tend to want to interact with plastics or rubber. Diazepam is lost from solutions when it's in contact with plastic packaging, so that has to be dealt with. So here we have an issue between an active drug and a formulation and the packaging conditions that it's under. Absorption of preservatives to rubber is a problem in injectable formulations when you have rubber seals in ampules and things. And they're enhanced when a drug or preservative is present at low concentration because the absence of the drug or preservative is noticed if a rubber seal takes it out of the formulation. So you have to bear that in mind. So now we're starting to move towards chemical stability, chemical instability, formulation instability, and the presence of all these components within a container and the context of which that formulation may be in, concentration within a solution and so on. So we are seeing elements now of being holistic, thinking about the chemical stability, physical instabilities, the cautions you have to take to preserve the actives and excipients. Now we're putting the compounds within packaging and starting to think, well, what might happen there? So you can see that formulation is an all-embracing topic, and you have to think a bit more widely about issues. And what you need to be aware of is really the inherent chemistry of the whole system. Again, pH, ionization state, and the unionized form of a drug or excipient is often less polar, and therefore can be attracted to rubber or plastic packaging. And a special procedure often is used to prepare rubber closures if you're going to use formulations in presence of rubbers. Evaporation can alter a formulation. So chloroform, which occurs within pharmacy on a not too infrequent basis, is not very effective as an antimicrobial preservative in liquid formulations due to evaporation away from those formulations. So they would have to be made up fresh. Glycerol trinitrate or nitroglycerine evaporates from tablets and can be lost by absorption into plastic packaging and can evaporate from that system by that means because it is a small, relatively apolar molecule. So often it's packaged in glass bottles with aluminium line closures to prevent this happening. Plastic packaging may be permeable to water vapour depending on the type of plastic. Plastics come in a whole range of properties, going from very, very hydrophobic to actually quite hydrophilic, but still polymeric, and permeability to water vapour is possible. So therefore water can be lost on long-term storage, and that concentrates the drug content, changing the nature of the formulation. The packaging can also have materials in it that help stabilize a plastic, allow the plastic to be processed into its shape, into the container's shape. And those plastics, those polymers, can have additives in that you have to be aware of. And when these have packaging, you can get what are called extractives. In other words, PVC, for instance, which is a flexible polymer and a common formulation container, can have plasticizers such as diethyl hexylphthalate, DEHP, which can migrate into injectable solutions over a long period of time. So the polymer container can lead to formulation decomposition by additives extracting into the formulation. And this is a particular problem when the solution contains non-aqueous solvents or even a surfactant that can encourage departure of this from the polymer. So paclitaxel, well, that's a mouthful, isn't it? Is administered in dilute solution by slow intravenous solutions, and it's contained in a polyoxyethylated castor oil to solubilize the drug, and ethanol as a co-solvent. It can't be added to infusion fluids containing PVC because DEHP is extracted from the PVC by this excipient, by this formulation. So glass or polyethylene containers can be used instead, and in an ICU, DEHP-free syringes and tubing, etc. has to be used. From glass containers can release hydroxide ions into an aqueous product, changing its pH because of the nature of the glass. Glasses can be soda-based glasses, or they've been formed by alkaline treatment of silicon dioxide, sand, to make the glass, and that can cause pH changes within a formulation. This can occur especially if you have heating in an autoclave situation of particular glass containers, therefore changing the pH of a formulation. Surface treated glasses are available to minimize hydroxyl ion extraction into formulations where this is of any serious concern. Microbiological stability. Microorganisms can make the product harmful to the patient or have an adverse effect on product properties, and microbial presence can deteriorate formulations and is a critical factor of sterility or sterile products when the container is opened. So this is why you get instructions to use once and dispose generally. So injections are used immediately, and then any residual materials are disposed of and not used a second time. Eye formulations have a short in-use life once opened, and we're probably, anyone that uses eye drops, including me, are probably guilty of using eye formulations above and beyond their shelf lives. And certainly you tend to carry them around with you, therefore they're not stored within a refrigerator, which is probably the best place for them.